Hey everyone! Welcome back to Learn Chem with Manasa. Today we're diving into something that makes carbon the superstar of chemistry. It's tetravalency. Ever wondered why carbon forms so many compounds? Let's break it down. Tetravalency simply means that carbon can form 4 bonds. That's right, carbon always forms 4 covalent bonds in its stable form. To understand why, let's look at carbon's atomic number. It's 6. That means 6 electrons. The electronic configuration is 1s2, 2s2, 2p2. Now in the outer shell, which is the second shell, there are 4 electrons, 2 in the 2s orbital and 2 in the 2p orbital. Carbon needs 8 electrons in its outer shell to be stable. That's called the octet rule. But it has only 4. So it forms 4 covalent bonds by sharing its 4 electrons with other atoms. Because of tetravalency, carbon can form single, double, or even triple bonds, and it can bond with other carbon atoms too. This is what makes organic chemistry so vast and fascinating. So, remember, carbon has 4 electrons in its outer shell. It shares these electrons to form 4 covalent bonds. That's called tetravalency, and this gives carbon the unique ability to form a huge variety of compounds. Hey everyone! Welcome back to Learn Chem with Manasa. Today, we're diving into the fascinating world of molecular shapes. The shape of a molecule affects everything, from how it smells to how it reacts. These shapes are predicted using a model called Weier's-Sepper theory, valence shell electron pair repulsion. According to VSEPR, electron pairs around a central atom repel each other and arrange themselves to be as far apart as possible. This determines the geometry of the molecule. So, lone pairs actually take up more space than bonding pairs. That's why, for example, ammonia is pyramidal and not flat, and water is bent instead of linear. Hi everyone, welcome back to Learn Chem with Manasa. Today we're unlocking a key concept in bonding hybridization of s and p orbitals. Hybridization is the process where atomic orbitals mix to form new, equivalent orbitals called hybrid orbitals. These new orbitals actually explain molecular shapes and bond strengths way better than just using normal atomic orbitals. Let's focus on how s and p orbitals hybridize. So, starting with sp hybridization, 1s, and 1p orbital mix together. This forms 2 sp hybrid orbitals. The shape here is linear, with a bond angle of 180 degrees. A classic example is beryllium chloride. Next up, sp2 hybridization, here, 1s and 2p orbitals mix. This creates 3 sp2 hybrid orbitals, giving a trigonal planar shape with a bond angle of 120 degrees. Boron trifluoride is a good example for this. And finally, sp3 hybridization 1s and 3p orbitals combine to give 4 sp3 hybrid orbitals. This arrangement forms a tetrahedral shape, with a bond angle of about 109.5 degrees. Methane is the go-to example here. Without hybridization, carbon would only make 2 bonds. But thanks to sp3 hybridization, carbon actually forms 4 identical bonds in methane, which perfectly explains the tetrahedral shape. Quick recap: sp means linear, with a 180-degree bond angle. sp2 is trigonal planar, with a 120-degree angle. And sp3 gives us that tetrahedral shape, with a 109.5-degree bond angle. Hybridization really makes bonding simple and shapes predictable. Hi everyone! Welcome back to Learn Chem with Manasa. Today, let's break down organic chemistry by classifying compounds based on functional groups. From the sharp smell of alcohol to the tang of vinegar, functional groups define how organic compounds behave. Let's explore the major families. A functional group is a specific group of atoms in a molecule that gives it characteristic chemical properties. Think of it like, the personality of the molecule. So, let's go through some of the main functional groups. First, we have hydrocarbons. Alkanes, which have single bonds, like for example methane, which is CH4. Next are alkenes with double bonds, such as ethene, C2H4. Then alkynes, which have triple bonds. An example would be ethyne, C2H2. Arenes, or aromatic rings, include benzene. Moving on, alcohols contain the O group. For example, ethanol, which is CH3CH2OH, and its functional group is called hydroxyl. Ethers have the structure ROR', like dimethyl ether CH3OCH3. Aldehydes have the CHO group, with formaldehyde HCHO as an example. Ketones feature a C double bond O group, such as acetone, which is CH3 COCH3. Carboxylic acids have the CO group, acetic acid CH3-CoA is a good example. Esters are R-CoR prime, like methyl acetate CH3-COH3. Amines include NH2, NHR, or NR2 groups. Methylamine CH3NH2 is one example. Amides have the CONH2 group, and acetamide CH3CONH2 is an example. Finally, nitriles have the CN group, like ethene-nitrile CH3CN. Here's a quick chart of functional groups, their general formulas, and examples. You can screenshot this for your revision. Functional groups are like building blocks. Once you know them, organic chemistry gets way easier. Got questions or need tricks to remember these? Just drop them in the comments. Hey friends! Welcome back to Learn Chem with Manasa. In today's video, we're diving into homologous series, especially those with halogens, oxygen, nitrogen, and sulfur. From alcohols to amines, each functional group forms its own chemical family, called a homologous series. Let's explore them with simple examples. A homologous series is a group of organic compounds with the same functional group, similar chemical properties, and a difference of -CH2 between consecutive members. Let's start with compounds containing halogens, F, Cl, Br, and I. These are called haloalkanes or alkyl halides. The general formula is CnH2n plus 1x. For example, chloromethane, which is CH3Cl, and chloroethane, which is C2H5Cl. The functional group is -X, where X is a halogen. These compounds are polar and, they undergo nucleophilic substitution. Now let's move to oxygen-containing families. Alcohols with the functional group -OH have the general formula CnH2n plus 1OH. Examples include methanol, CH3OH, and ethanol, C2H5OH. Ethers have the structure ROR prime, like dimethyl ether, CH3OCH3, and methoxyethane. Aldehydes have the -CHO group, for example, formaldehyde, HCHO, and acetaldehyde, CH3CHO. Ketones have the -CO- group, like propanone, CH3COH3. Carboxylic acids contain the -COH group, such as formic acid, HCO, and acetic acid, CH3CoO. Esters have the -core group, for example, methyl ethanoate, CH3COH3. Next up, compounds with nitrogen. Amines have groups like -NH2, -NHR, or -NR2. Examples are methylamine, CH3NH2, and ethylamine, C2H5NH2. They act as bases and nucleophiles. Amides have the -CONH2 group, such as methanamide, H-CONH2, and ethanamide, CH3CONH2. Nitriles contain the -CN group, for example, ethene-nitrile, CH3CN. And finally, sulfur-containing compounds. Thiols, which are like alcohols but with sulfur, have the -SH group. Examples include methanethiol, CH3SH, and ethanethiol, C2H5SH. Thioethers have the RSR prime structure, for example, dimethyl sulfide, CH3SCH3. So, all these homologous series, they differ by these CH2 units and, show a gradual change in physical properties, like boiling point solubility and even molecular mass. And hey, as you continue your chemistry journey, this video will give you the clarity and confidence to move ahead. Hey everyone, welcome back to Learn Chem with Manasa. Today, we're going to talk about a super important and, slightly tricky concept in organic chemistry: isomerism. Why does C4H10 exist as both butane and isobutane? Same formula, but totally different structure and properties. Let's break down the magic of isomers. Isomers are compounds that have the same molecular formula, but different structures or spatial arrangements of atoms. And that gives rise to different properties. Structural isomers differ in the way atoms are connected. There are several types. Chain isomerism. That's when you have a different carbon chain arrangement. For example, butane, which is CH3CH, 2CH, 2CH3, versus isobutane, which is CH3CH, CH3, CH3. Next, position isomerism. Here, you have the same functional group but in a different position, like but1-ol versus but2-ol. Then, functional group isomerism. Same molecular formula but different functional groups. For instance, ethanol, which is C2H5OH versus dimethyl ether, which is CH3OCH3. There's also metamerism. That's when you have different alkyl groups on either side of a functional group like O or NH. An example would be CH3OCH2CH3 versus CH3CH2OCH3. Finally, tautomerism, which is a dynamic isomerism. like ketoenol tautomerism, where CH3-COH3 is in equilibrium with CH2 equals COCH3. Now let's talk about stereoisomers. They have the same bonding sequence but differ in the spatial arrangement of atoms. There are two main types, geometrical or cis-trans isomerism, which happens in alkenes or cyclic compounds. For example, in but2-ene, you have cis-but2-ene where both CH3 groups are on the same side, and trans-but2-ene where the CH3 groups are on opposite sides. The other type is optical isomerism, which occurs when a molecule has a chiral center, usually a carbon with 4 different groups. An example would be lactic acid or 2-butanol. These isomers are non-superimposable mirror images and rotate plane polarized light differently. Here's a quick summary of isomer types. Structural isomers have different connectivity, while stereoisomers have the same connectivity but a different spatial arrangement.